Today's review day. So we're gonna go, I'll go pretty quickly with you guys. We're gonna talk about, real quick, review real numbers, kind of sets of real numbers, subsets of real numbers, properties of real numbers, and then we'll probably push on and maybe do, just kind of remind ourselves how we use order of operations. And just a really basic, probably haven't thought about a ton of math over the summer, so we'll ease back into things a little bit, okay? So first of all, real numbers. Let's talk about how we dissect the set of real numbers for our use in an Algebra 2 class. What are real numbers? Numbers that aren't fake. Okay, numbers that, okay, we'll go, numbers that are not imaginary. Okay, good. So you guys have talked about imaginary numbers a little bit?
Just like what?
Like
Mrs. Jones is like imaginary numbers. That's
Oh,
it.
that.
Okay, so for now, that's fine. So you know of the existence of some non-real numbers. Okay, good. And they're out there, we'll talk about them. But everything you've ever used, any number you've ever really used has been a real number. Okay, and we'll get to non-real numbers here, fairly quickly, but not till well after roundup, okay? So the set of real numbers, every number we've ever used. What's our definition, just quick and simple definition of a set in mathematics? Or in any, doesn't even need to be in mathematics. What's a set? A group. Okay, it's a group of, in math, to be more specific, we'd say a set is any grouping or group of elements. Elements could be numbers, it could be other things. To pick a non-math example, we could talk about the set of all the dishes in your house at home, okay? We'll come back to that. What's a subset? Say it again. A group within a group, okay, or a set within a set. It's a smaller set that's included within a larger set, okay? Give me an example of a subset of the set of dishes in your house. All the bowls. There you go. Okay, all the bowls, right? Would be a subset of the set of all the dishes. It's completely contained within the set of dishes, but it doesn't include, there are other dishes that aren't bowls, okay? So the primary subsets that we talk about for real numbers, just a very quick review, you've all seen these. The set of natural numbers is the set of counting numbers, right? So it's the set of 1, 2, 3, etc. What is the smallest element in the set of natural numbers? 1. 1 is the least element in the set of natural numbers. What's the greatest? There isn't one, is there? Right? They get infinitely large. Okay? So there's an infinite set of natural numbers. We'll kind of talk a little bit today about infinity. I could spend a whole year teaching you about nothing but infinity, and we'd never do the same thing twice. It's a huge topic, no pun intended. But we'll touch on it a little bit today. So one other thing I'll just point out is in math, we want to use very particular notation. In math, our goal is to be able to express a lot of unambiguous information that is not open to interpretation. There's one meaning that we all understand. We want to do that efficiently. We want to do it using notation and rules that make sense to everybody, right? So let's kind of start that process today, and we'll continue it throughout the year. Do you understand that when we describe a set, one way in math to talk about a set is using what's called set notation, where we end up with these script brackets. When you see a set of script brackets, you're always thinking set, right? That's enclosing some stuff. In this case, it's enclosing all of the real numbers, 1, 2, 3, etc. And when we say something like that in math, that ellipsis, what does that imply? Goes on and on and on, etc. Following that pattern, right? So how is the set of whole numbers different from the set of natural numbers? Okay, all we do, it's the set of natural numbers plus 0, right? So it only adds one additional element, but it's bigger, okay? Would you agree it's bigger? Okay, how much bigger? 1. How big is the set of natural numbers? It's infinite, right? An infinite number of elements. How big is the set of whole numbers?
Plus 1.
Well, infinite plus 1 is just infinite.
Yeah.
See, here's our first seeming paradox, right? They're both infinite sets, and yet the set of whole numbers is 1 bigger than the set of natural numbers, right? Is that a weird concept? How can you have two sets that are both infinitely large and yet one set is bigger than the other one?
If it has no end, then technically neither is bigger than.
Okay, but it is bigger.
The beginning is.
But in math, you go ahead.
That was like a zero. Does that make it bigger?
It's the zero is what makes it bigger, but how would you, and this gets into the part of math where, I mean, you could argue both points to a non-mathematician and sound pretty darn good. And I bet you could have a vigorous debate, and you could, depending who's the better debater, you might be able to convince somebody that these sets are the same size or that the set of whole numbers is bigger. It might, but in math, it's unambiguous. We know that the set of whole numbers is in fact bigger than the set of natural numbers. Now, any idea how maybe you could prove that? I'm going way off script here, but I'll do that a lot with you guys.
No matter how many you go, there's always that extra zero on whole numbers in
Okay.
that group. It's only a select group of numbers.
Okay, that's the right idea. Now, the way we could maybe go into a more rigorous proof, I'm not gonna write out a rigorous proof here, but we could do something like this. You could map or assign a one-to-one relationship between each of those numbers, couldn't you? And so on and so forth, right? You can map all of the natural numbers to the whole numbers, except there's one that won't work. There's an additional number that does not map between the two sets. And because you've got this one-to-one mapping in these sets, and you have an additional one in the whole numbers, it's bigger, right? Regardless of how far you carry this out, you're always gonna have one extra one here, right? So that's one way you can maybe show that. Okay. What about the set of integers? What does that add to the picture then? Negatives. Like we could say maybe negative whole numbers or something, right? Okay. And you can think about obviously the set of integers as being, the hash marks on a number line or something like that, right? You've got the negative integers and the positive integers, and 0 is the boundary between the two. It's neither negative nor positive, okay? Good. What about rational numbers? Tell me what you know about rational numbers. Think back to, and you may not give me the whole picture, but just tell me something you know about rational numbers. Okay, they don't need to be whole numbers. Could they be whole numbers? Yes, they could. Okay, but they could be fractions that are not whole numbers. Let's try to make this more compact. Yes.
They can be written in decimal form, and they can also be like 1, 5, and stuff like that. Wow. Like, instead of having it in a fraction.
Okay, good. So I'm going to come back to that. That's a good one, though. They can be written in decimal form. We can write any number. We can represent any number as a decimal, right? But there are some specific things that happen when we represent rational numbers as decimals, and I'll go right back to that point in a second. You fill in the blank for me. A rational number is any number that can be written as a fraction. There you go, right? Okay, and we can see that right in the title of the word. It's a ratio number, right? Ratio means fraction. So any number that can be written as a fraction is a rational number. Now let's look at how we would say that mathematically. Right, using mathematical language. This says all the stuff that we just said there, right? So what does the script brackets part tell us? The setup. Okay, so right away we've got something, and we can kind of turn this into words, right? If we wanted to say this mathematically, this part right here would read the set of, what comes next? M over N. Okay, there's the next part. Okay, how about that vertical bar? What does that mean in math? That's one you've probably never seen before. It shows up in math, it shows up in programming, which is really just math. Coding. It means such that, and then it always means there's going to be some condition that follows that, right? You could say if or such that. I always say such that because it just seems like it flows better. You could even say something like with the condition that or if or something along those lines, and then we just get the rest of it is just the statement that follows that. So we'd read that as the set of m divided by n such that m and n are integers and n does not equal 0. Okay? Now let's look at that last part. How do you build a fraction? You have a what divided by a what? Integer divided by integer, right? So that part makes sense. So we're dividing m by n such that m and n are integers. What about this very last piece over here? That n does not equal 0. Why do we have to tack that on? Can't divide by 0. There you go, right? There's two fundamental no-nos for real numbers that there's two rules we'll always follow, and you know them both. One of them is you can't divide by, what's the other one? Can't take an even root of, I can say a square root for that. Can't take a square root of, no, square root of 0 is what? Square root of 0 is 0. Square root of 1 is 1. You can't take the square root of something. A negative number. You know, we're not going to concern ourselves with that one so much right now, but the dividing by 0 one is important here, right? So we have to include that little bit of information. M and n can be any integers, but things blow up if n is 0, because that forces us to divide by 0, which we can't do, right? Okay, so earlier it was mentioned that rational numbers, if they're written as fractions, we always get one of two outcomes, right? If we turn a rational number into a fraction, we always get two outcomes. Either the decimal, or sorry, into decimals, not fractions, what am I saying? Let's fix that. Either the decimal is going to do what? What or what? It's either going to terminate. For example, 1/2 equals 0.5, period. Exactly, right? Or, how do we describe that? Oh, you said it repeats. There you go. So for example, 1/3 equals 0.3 and the bar means repeating. Okay, good. What if I wrote a number like, what does that mean? Oh, the last 3 digits just repeat. That's the pattern that repeats. Good. So you know all this stuff. Good. Okay, so then if we say that a rational number is any number that can be written as a fraction, how do we describe an irrational number? A number that can't be written as a fraction. Okay, now this is an interesting relationship. If we look at, I'm going to use a Venn diagram here. We'll kind of go back and forth just a little bit. Whenever you describe sets using kind of like visual aids like this, as being, you know, these groups that we can see visually. Usually they're kind of like these ellipses. They could be boxes or whatever though. Whenever we do that kind of thing, that's called a Venn diagram. I'm sure you've probably heard that before, but if not, no big deal. Whenever we do that, it's useful to us because it helps us to see visually what the relationships are between these sets. Sort of conceptualize this a bit, right? So let's look at the sets that we've already talked about. So we're going to let the set capital N represent the set of natural numbers. We'll let the set capital W represent the complete set of whole numbers. Now let's focus on that for a second. So the set of natural numbers is this infinite set, 1, 2, 3, etc., right? So why do we have a 0 there? Because that's the only other element that is included in the set of whole numbers, but not in the set of natural numbers. right? But you can see that the set of natural numbers is a subset of the set of whole numbers. It's a nice way to see it visually, isn't it, right? So the set of integers includes the set of whole numbers, but there are some elements of the set of integers that are outside of the set of whole numbers, and those would be the negative natural numbers, right? Make sense? But there, once again, you get this nested look, right, where the subsets are nested within the supersets, right, the bigger sets. And then it goes all the way out to the set of rational numbers. Oh, and by the way, one little change we'll make too. I pulled this off of somewhere, but usually we don't use a capital I. The letter that we use to represent the set of integers is usually a capital C. Let's make that change. And then the set Q is the set of rational numbers, right? So what are all the elements of rational numbers that are outside of the set of integers? Well, we've already kind of talked about it. Fractions that can't be written as integers, right? So fractions of the form m over n, where n does not equal 0, and the fractions don't reduce to an integer, right? Okay, but look at the relationship. If we're saying that the red box represents the complete set of real numbers, this set of rational numbers is a subset of that, but what about the set of irrational numbers? How is that related to the set of rational numbers? Is it the same kind of relationship we had here? We could say that the set of integers is a subset of the set of rational numbers. Is the set of rational numbers a subset of the set of irrational numbers? You're right. How come? Yeah. What's going on? They're not the same. They're different. They're mutually exclusive, right? If you're one, you're not the other. Okay. So we'd say then we call it Q prime. Prime means opposite of or different than, right? Or not. So the set of Q prime, really that just means the set of not Q. It's all the real numbers that are not rational numbers are irrational numbers. So it's a separate set that sits outside of the set of rational numbers so that neither one is a subset of the other. Okay? So going back to this thing about irrational numbers. So here's the way we can say this in math, one way. Irrational numbers are the set of H such that H is not a rational number. Another way you could do that is you could say it like this. If I were programming, I would probably say it like this. The set of H such that H is not an element of the set of Q. So anything that's not in Q, not an element of Q, represents Q prime. Okay? Something like that. Okay? All right, so what if I represent irrational numbers as decimals? What has to happen? Describe what the outcome has to be. There you go. As decimals, they don't repeat and they don't terminate, right? So if we want to kind of just fill in a little summary then of what we talked about, and this kind of goes back to our well, I don't even want to spend a lot of time on this stuff with you guys. I mean, if I were to turn these into decimals, do you see that I'm going to get, obviously, these are all rational numbers, aren't they? So we know the decimals have to repeat or have to terminate. Negative 5/7 works out to be negative this big long group of repeating numbers. That's what you find. Put it in a calculator. 15 over 5 is just 3. 3 written as a fraction or as a decimal is just 3, right? It's an integer. And then 13/25 ends up being a terminating decimal. Okay. What about these? Rational or irrational? A. Rational. Square root of 25 reduces or simplifies to just 5, doesn't it? So as a decimal, it's 5. 33/9, rational or irrational? It's a fraction. It's rational, isn't it? That one's an easy one. Square root of 11. Irrational. What's the difference, real quick, between square root of 25 and square root of 11? Why is the square root of 25 rational and the square root of 11 is irrational? 25 is a what?
Exact.
Yeah, what do we call that? A number that's
Perfect
Perfect square, there you go, 25 is a perfect square and 11 is not, good. 17/34, obviously that's rational. What about the bottom one? Irrational. It's kind of tricky, it sort of looks like it wants to be rational. There is a pattern there, isn't there? But it's not a repeating pattern, so it's irrational. Good, okay? All right, so quick summary then, here's another way we could represent those sets if you wanted to, same information. This stuff will all be up in my notes if you want to take a closer look. But once again, you've got the complete set of real numbers broken into the green set of rational numbers and the different, mutually exclusive set of irrational numbers. And then within the rational numbers, we've got some subsets that are nested, okay? Here's even another way to do it. We'll come back to this one later when we get into complex numbers with imaginary parts. We might come back and take another gander at this little picture and make sense of it. It's really good. It does a lot of stuff. There's a lot of organization that you don't even see at first when you look at this. But for now, it's probably overkill. Okay, so what do we represent? I didn't say this, but what do you suppose how do we represent the set of real numbers, capital R, good. And then we already said all this stuff, the set of irrationals, that's Q prime, rationals, Q, integers, we said C, whole numbers W, natural numbers N. What are some quick examples? Irrationals? Pi, square root of 2, stuff like that, right? As decimals, it would be something like 1.35793, it goes on and on without repeating, right? What about rationals? M over N, where they're both integers, would be a quick way to say it. If we're looking at specific examples, what would be specific examples of rationals, of different kinds of rationals? 1.75, terminating decimal. Good. What's another one? Say it again. 1/3. Okay. Square root of 25. Good. I could do something like square root of maybe 1/4, right? That would reduce to 1/2. Would you agree? Okay. I could do 0.3 repeating. Those are all examples, right? Integers, well, I mean, now we're getting down to, really at this point, oops. We'll just write the set down. Whole numbers start at 0. Natural numbers start at 1. Etc. So there's all our stuff, right? Okay, next issue. Okay, real quick. We'll just do like 2 of these. This will be easy. Number 1, we want to write all the sets to which each value belongs. Now, what would be probably the best way to do this? Where would we start? Okay, we'll start with the smallest set, and then it'd be everything that includes that smaller set, right? So the smallest set that includes -10 would be what? Integers would be the smallest set. It's not included in the set of whole numbers or natural numbers, right? So we start with a Z, and if I can write a Z in there, what else am I guaranteed to be able to write? Q, good. If it's an integer, it's guaranteed to be rational, and if it's rational, everything's guaranteed to be real, right? Okay. How about square root of 30? Q prime. And then the only other thing that would show up every time would be what? Real, yeah. They're all real numbers, aren't they? Okay. What about pi minus pi?
Whole number.
It's a whole number, so then it would have to be an integer and a rational and a real. You get the idea. Okay, properties of real numbers. Let's have a look at these. So, real quick, justification for why we maybe go through these. You probably remember these, but you may have forgotten some of them too. 2 things I'll say about this. Something I want to reinforce all the time in math that's going to help you be a good student in any class you take. And it just helps you helps you retain information and make sense of it at a higher level, so you're able to use the information better. General rule, try not to remember things in terms of facts. Okay, I once knew all 50 state capitals. I probably know like 5 of them, if that. How come? Who cares? It's not that big a deal, right? I got stuff that's Googleable now. So why do I need to know that stuff? I don't want to clutter up my brain with useless information because, contrary to popular belief, you do fill your brain up. Your brain is, you've probably heard the myth that you only use 10% of your brain. That's not even close to true. You use 100% of your brain pretty much all the time, right? It doesn't mean that you don't have the capacity to increase the amount of knowledge in your brain, but your brain does pare things out. Have you ever seen like people on, probably seen on TV, people that remember everything, right? And they have photographic memories.
Yeah.
And it might seem like that's a pretty good thing to have, but it's not. How come? It's not if you want to be, say, a mathematician or a
Because
physicist.
there's so much stuff that you remember all the time that you can't maybe find the thing that you're looking for.
Well, for one thing, there's so much stuff you remember all the time that it's hard to maybe catalog it. But there's another aspect of that too. If you're using your brain all the time to remember individual facts, it makes it more difficult to use your brain to do higher level thinking, right? Because your brain is sort of bogged down by all these extraneous facts. And your brain naturally has evolved to get rid of stuff. It takes out the trash, so to speak. So you do forget things that you don't need very often, and that's not a bad thing. That's generally a good thing. It means you're opening up room for doing more important thinking in your brain, right? I don't want to clutter my brain up with a bunch of useless facts, and so I rarely ever remember stuff, memorize stuff. And really, honestly, I'd say that any kind of learning that you do that's factual-based learning is extremely low level, and it's almost not even worth doing. It's really not. I know there are some classes where you're going to have to just memorize stuff for a test, but then what do you do? As soon as you memorize all the state capitals, what do you do immediately? You start to forget about it, right? Because who cares? Instead, what you want to do is you want to try to attach things conceptually in your brain. You want to interweave ideas and concepts rather than try to memorize facts. And then you never forget stuff. And I'll point this out throughout the year, but I don't remember. I never remember like teaching calculus. Do I remember all the trig identities? Well, if I'm using them a lot and they're in my working memory, then I do. But I take the summer off. Do I remember all the double angle formulas and the half angle formulas for trig? No, I don't. But I can derive them for myself within 30 seconds because I know the big relationships in trig. And so I can always take a piece of paper and do a quick derivation and figure out what they are, right? To me, that's much better. It's there at a deeper level. I got to do a little thinking to retrieve that stuff or recreate it. But it's not like it's just hung in there in little bits of your brain where it goes away easily. Something that's interesting to look at. What do you think happens if you take a person's brain and you do a real-time PET scan, where you're going to look at the activity in their brain via the heat signatures or the electrical activity? What if I ask somebody to think about, to say, what's the capital of New York? What is that, Albany? So if I say, what's the capital of New York, and they say Albany, and you look at their brain, how much of their brain do you think lights up? Tiny little bit, not very much at all, okay? Now, if you ask somebody to solve an algebra equation, and you look at their brain, what happens? It lights up all over. There's this huge network of interconnected neurons. They're connected by dendrites and axons, and there's like this rippling effect where you see this activity all over. It even spans from the different hemispheres of your brain. Crosses that corpus callosum, and it's all over your brain. So which one do you think is easier to hang on to, the ability to solve an algebra equation or remembering what the state capital of New York is? The algebra one, because if little pieces of that network go away, you can still recreate the network pretty easily. Most of it still is there, right? You get the idea? Okay, so that's a long story for kind of a short application, but I want to get that out early in the year because that's something you want to challenge yourself to try to do. So what about these, the commutative properties? If you just remember that, like a flashcard, on one side is commutative property, on the other side is this equation, you're going to forget it, right? But if you can attach it to a concept you're familiar with, you'll hang on to it. I'll do that for you. And you can kind of try to do this more for yourself, but Here's just one, here's how I do it. What does it mean to commute? Think about the meaning of the word commute. When your folks commute to work, what do? They travel. They start off at home, and then later in the day they're at work, and then at the end of the day they're back at home, right? So what are they doing? They're just exchanging places. That's all it means to commute, is to interchange or exchange places. So the commutative properties just say that when I'm adding two things together or multiplying two things together, I can commute the positions of the terms in the sum or the factors in the product. A plus B is the same as B plus A. It makes no difference, right? 2 plus 5 equals 5 plus 2. Agreed? 3 times 4 equals 4 times 3, right? It works for addition and multiplication. What about subtraction? Does not work, does it? For subtraction, if we do something like 17 minus 5, that's different than 5 minus 17. What about division? Doesn't work, right? 20 divided by 5 is different than 5 divided by 20. So the commutative properties of addition and multiplication just say that the order in which I add or multiply two things is irrelevant. Okay? We can exchange the positions of those two players in either equation. Okay? What about the associative property? What's it mean to associate? Who do you associate with? Your friends, probably, right? If you're in a business, you have business associates, so the people, the other business people that you group yourself with, right? So to associate means to group. How do you, real quick, do this in your head. What's 2 times 3 times 4? 24. How'd you get it? 2 times 3 is 6 times 4, right? Probably most people did. Okay, there's two morals to that story. You must multiply things in pairs, first of all, right? Products always occur in pairs. We don't think about 2 times 3 times 4 all at once, right? We think about 2 times 3, get an answer, times 4. Anybody else do it differently?
3 times 4.
Okay, 3 times 4 is 12, times 2 is also 24. What's the moral of the story? It's no different, right? You can group the products in any order you want to. If I'm multiplying A times B times C, I can group the B times C, or I can group the A times B, or I can group the A times C first. It makes no difference, right? We can group or associate factors in any order we want to when we're multiplying more than two things. Okay, same for adding, right? A plus B plus C, I have to add things in pairs, right? So either I can do the A plus B first and then add C, or I can do the B plus C first and then add A, right? That's the associative property. The way we group more than two things for addition and multiplication is irrelevant. As you might have guessed, though, and you probably already know, it doesn't work that way for subtraction, does it? 8 minus the quantity 3 minus 15 is different than the quantity 8 minus 3 minus 15. The way I group those gives me different results, and so that we would say that numbers are not associative or subtraction or division, right? 64 divided by the quantity 8 divided by 4 is different than the quantity 64 divided by 8 divided by 4. You get different results, okay? All right, the next two. Distributed, we can pretty much skip this, can't we? Right? We just know that if we're multiplying something by a sum or a difference, by a quantity, we can just distribute over the sum or the difference. Right? No big deal. How many times have you seen teachers do this in class? Right? You're just distributing the A to both parts. Okay. We'll skip through that. No big deal. Okay, these other two, though. Oh, what's being distributed here, real quick? -1. Same thing here, right? Okay. Okay, what about these? The identity and inverse properties. Really simple stuff, but they're strongly connected. And it's really boring probably for numbers. It's just pretty boring and obvious. But I want you to just be aware that there are other things beyond just real numbers or even complex numbers that we can apply this stuff to. Like you could, for example, we could talk about vectors or matrices. Like if I were going to do something like, let's say I'm going to define, and this isn't a regular, this is kind of an honors algebra 2 topic. I will show you guys a little bit of this at the end of the year. If we take the matrix with the elements 1, 2, 3, and 4, it's a 2 by 2 matrix, that represents a lot more information than just a single number. there is an identity matrix that we can multiply that by, and it does the same thing that we're gonna talk about for numbers, right? Now, for numbers, if we're adding numbers, what's the identity number? What's the number I can add to something and preserve its identity? 0, right? Obviously, right? So that's the additive identity, is what we call 0. Add that to anything, it doesn't change the identity, right? What is it for multiplication? 1. So the multiplicative identity is 1, okay? What is the multiplicative identity for a matrix? Well, it's the identity matrix. So for a 2 by 2 matrix, instead of multiplying by 1, we'd multiply by the identity matrix and we'd get back the same thing we started with, okay? You don't know about that stuff yet, but the point is, this relationship extends beyond just simple numbers, okay? The identity matrix for addition would just be 0, 0, 0, 0. And you'll see later how that all works. Okay, what about inverse? So the inverse properties and the identity properties are strongly linked. We identified the special identity number for addition is 0. The special identity number for multiplication is 1. Okay, now, to find the inverse, we're going to say if I start with the number a, what could I add to that and get back my special additive identity, 0? So a plus blank equals 0. Negative a, right? What about for multiplication? Same deal. We're going to start with the number a, and we want to ask the question, I could multiply by what? Fill in the blank to get as the result my multiplication identity number, 1. So a times what would equal 1? That's a tougher one. 1 over a. Okay? What do we call that? It's the multiplicative inverse is 1 over a, but we give it a special name. If I take a fraction, a, reciprocal. There you go. And what's the additive inverse? If I take a number and I add to it something to get 0, you said it was negative a. What do we call that? It's the additive inverse, but we give it a special name. Now turn the page and it'll maybe make more sense. So here's our additive inverse, right? A plus negative a is 0. So the additive inverse is right there. What do we call that? Opposite, sure. So negative 7 plus 7, its opposite would be 0, for example, right? We already said that the multiplicative inverse is just a reciprocal, okay? Is there an inverse for matrices? Yeah, there is. It's called an inverse matrix. If we take a matrix and multiply it by its inverse, I'm going to get back, instead of 1, I'm going to get back that crazy identity matrix. Okay, so that stuff works for other things too. Okay, we could probably dispense. I'll put all this stuff on Moodle if you need to look at it, but I don't think you will. What's, just really quickly, what property is being demonstrated right there? Everybody take a look. So it'd be the associative, good, it's the associative property of what? Of multiplication. So I'm just going to put a little multiplication sign about it, okay? What would this be? Inverse property of addition. You get the idea? How about this one right here? Commutative property of addition. Okay? Name the, we're looking at inverses here. What's the additive inverse of negative 8? Positive 8. What's the multiplicative inverse? 1 over negative 8, which we could simplify maybe to just negative 1/8. Okay? Oh, not done. Okay. All right, so I'm not going to give you the worksheets. There'll be a Moodle assignment going up probably tonight. You can start it tonight. It won't be due until like end of the weekend or something.
Are
So
we just working on these tomorrow?
we'll just continue. Yeah, we'll continue more review tomorrow. Yep.
So it's not homework?
No, those are just anything I give you that's got 3 holes stapled in it. I don't want from you. Those are just for your notes. Okay. Trey,
What happens?
what do you know? Huh? What do you know? That much?
Yeah.
Yeah.
You guys do you have honors?
Yeah.
2 or 3?